Hello, good evening everyone. To those who are joining today for the first time, my name is Akhil and I am currently a PhD scholar in IIT Madras. We are currently doing this weekly sessions for the course Machinery, Fault Diagnosis and Signal Processing every week in Saturday 7 to 9 p.m. And this is my email ID. If you have any questions, you can email directly here or you can post in the discussion forum also. And these sessions will be uploaded, the live sessions will be uploaded in YouTube in this playlist. And yeah, the links of which will be uploaded in a Google Sheet which is already shared with all the students. Okay, so yeah, let's begin the today's session. Yeah. So the first question, an analog signal contains usual frequencies up to 300 Hertz. What is the request rate of sampling for this signal? So can anyone give me the answer? This is one of the questions which we have seen multiple times in the last weeks. So anyone? We have frequencies of up to 300 Hertz. So what should be the Nyquist rate? So Nyquist rate is basically sampling rate. So what is the advised sampling rate for this case? Yes, 600 Hertz. Yeah. So if the maximum frequency available is 300 Hertz, then you should sample it at least 2 times the maximum frequency, right? So 600 hertz. So you can actually sample it at 1200 hertz also, but Nyquist rate corresponds to the minimum frequency at which you should sample. So here the answer is 600 hertz. Okay. Yeah. So even if you sample at 1200 hertz, you will still be able to track all the properties of the signal. But you don't need to do it at that high frequency. If you just do 600 hertz, that's enough. Yeah, that is for this question. I hope this is clear. So yeah, let's look at the second question. So an analog signal has useful frequencies of up to 240 hertz. Okay. Suppose we sample at a rate of 600 samples per second. What is the highest frequency that can be represented uniquely? So we have a signal which has frequencies of up to 240 hertz, but we are sampling at 600 samples per second. Is that enough? 600 samples per second for 240 hertz? Following the Nyquist rate or the sampling rate we know, is that enough? You can answer, you can unmute and answer anyone. For a frequency of 240 hertz, is sampling at 600 samples per second enough? So you need to sample only at 480 hertz, that should be enough, but you are sampling at 600 second, 600 So it is enough, right? 600 greater than 480. So if you sample at 600 hertz, that should be enough. Now, let's say if you are sampling at 600 samples per second, what is the highest frequency that you can actually represent uniquely? For this sampling rate, what is the highest frequency possible? Any answer? So you are sampling at 600 hertz. So anything of 300 hertz, 600 by 2 hertz, you will be able to track, right? Is this clear? Is this question clear? I hope. Okay. So here this 240 hertz, this data is just to deviate you from the correct things. So here the question is, what is the highest frequency that can be represented if you are sampling at 600 samples per second? So if your sampling rate is 600, then the maximum frequency you can get is half of the sampling rate. So 300 hertz. Okay. Yeah. Uh, yeah. I hope this question is clear to the others also. Now let's move to the next question. Okay. So here we have a handheld accelerometer calibrator provides 20 meter per second square of peak vibration in terms of acceleration at a circular frequency of 2000 radians per second. Okay. And calculate the linear frequency and RMS amplitudes of velocity and displacement. Okay. So here I'll wait for 1 or 2 minutes for all you also to read the question and understand. And then I hope one of you can actually maybe explain what we should do here. Mhm, have you understood the question? What was asked? Okay, so let me go into details of the question. So they have given acceleration at a peak as 20 meters per second square. Okay, so they have given us the peak acceleration of 20 meters per second square and at a circular frequency of 2000 radians per second. So what is the simple wave equation or yeah, periodic wave equation which we use? A sin omega t, right? So A is the amplitude, for x being the displacement and omega is the circular frequency here in a sin omega t, and t is time. Now what they have given is, they have given us the peak acceleration and the circular frequency omega. So they have given us omega is equal to 2000 rads per second and acceleration. So how will you get acceleration from the displacement? So if you do first derivative with time, then you will get velocity a sine derivative cos omega t, omega will come, okay, and acceleration cos derivative is minus sine and omega will come again. So right, so this is the acceleration amplitude, this is the velocity amplitude. So let's write those. And velocity amplitude would be a into omega and acceleration amplitude. So minus OA omega square, but if you are looking at the amplitude, so only the magnitude is enough. So A omega square, okay. Now they have given us the amplitude or the peak for the acceleration. So that means they have given us this. Okay. So we know omega and we know A omega square. So then can we calculate A? We can, right? So A omega square is 20 meter per second square and A omega is 2000 radians per second. So 2000 so A into 2 to the 4 into 10 power 6. So radians square it's dimensionless. Okay. So second square gets cancelled. A is equal to 4 5s are 20. So 5 into 10 power minus 6 meters. So A is equal to 5 micrometers. Okay. So now we got the displacement amplitude here. What are we asked? We were asked to calculate the linear frequency and the RMS amplitudes. Okay. So first let's calculate the normal amplitudes. Now we got the displacement amplitude. What would be the velocity amplitude? A omega, right? 5 into 10 power minus 6 meters into omega is 2000 radians per second. So 5 2s are 10. 10 power minus 6 into 10 power 3. So 10 power minus 3. So 10 mm per second. Okay. So we got the displacement amplitude and the velocity amplitude. And first thing is linear frequency. So how is circular frequency and linear frequency related? So the circular frequency is equal to 2 pi f, right? Yeah. So this is circular frequency and this is linear frequency. So f is equal to omega by 2 pi. Omega is 2000 by 2 into pi is equal to 1000 by pi. So some 318 point some hertz. Okay. So this is the linear frequency. Now we want the RMS amplitudes of velocity and displacement. So you know the amplitude. So what would be the RMS amplitude? Anyone? Yeah, exactly. So RMS of displacement amplitude would be a by square root 2. So 5 by square root 2. Yeah. So it's around P.536 micrometers. Okay. Now similarly, RMS of velocity amplitude would be a omega by square root 2. So basically velocity amplitude by root 2, which we already calculated velocity as 10 mm per second. So 10 by square root 2 mm per second. So this would be around 7.07 mm per second. Okay. So is this question clear now? How we calculated from whatever was given? So these questions you can basically assume, or you can basically look at this relation where displacement amplitude, velocity amplitude and acceleration amplitude in terms of the displacement amplitude and the circular frequency omega. So if you know these three formulas, which are just derived from a sin omega t, which you can also do if you have time, then you can solve these kind of questions. And for RMS, just by square root 2 of amplitude will be the RMS. Okay. Is this clear? So first we based on whatever was given, we calculated the displacement amplitude A and the circular frequency. From these two, we have then estimated the velocity amplitude as a omega and the acceleration amplitude is a omega square. So from that we got A, that is basically displacement amplitude. From this A and omega we calculated the velocity amplitude, and from omega we also got the linear frequency as circular frequency is equal to 2 pi f. Okay. I hope this question is clear. If you have any doubt, you can ask now and we can discuss further. Okay. Then we'll move to the next question. So the acceleration of a signal is given by a of t is equal to minus 20 sine 2t. Find the circular and linear frequencies and the signals of displacement and velocity. So this is very similar to the last question, but instead of the displacement signal, we have the acceleration signal directly. So will you be able to estimate this question? I'll give you 2 minutes to work it out and then one of you to explain the solution. This is very similar to the last question. So the hint lies in this equations. Is anyone able to come up with the solutions? Rajesh, you can unmute and speak. What about Samir and Sonal? Okay, okay, Sonal. Yes, circular frequency, yeah, 2. Okay, and can you derive the signals of displacement and velocity? So in our last question, what we derived was if x of t is a sin omega t, then displacement, that is displacement, velocity would be a omega cos omega t, and acceleration would be minus a omega square sin omega t. Okay, right? So this part is clear, right? Now they have given acceleration is equal to minus 20 sin 2t. So if you equate on both sides, a omega square is 20 and omega is equal to 2, right? So from these two, so I'm just equating this to this and omega here to omega. Okay, from these two, now we can get a into 2 square 4 is equal to 20, a is equal to 5. Okay, so now we know a and we know omega. So now can we write the signals of displacement and velocity? So velocity signal is a omega cos omega t. So 5 into 2 into cos 2t is equal to 10 cos 2t. Okay. Now that is velocity signal. What about the displacement signal? Is a sin omega t. A is 5 sin 2t. So this is the displacement signal and this is the velocity signal, right? Now we have done this. What is the linear frequency? So omega is equal to 2 pi f and f is equal to omega by 2 pi. So 2 by 2 pi 1 by pi. Okay. So now is it clear? So based on only the acceleration signal, we estimated the signals of the displacement and velocity and the linear frequencies also. So is this clear? how you can, let's say if your signal is given, how you can estimate the other corresponding signals. So similarly, if you are only given the velocity signal or the displacement signal, you can construct the other two signals and calculate the necessary terms. Okay. Uh, is this clear? This point? Yeah. So let's move on to the next question. A pure tone signal of 1000 Hz is to be digitally acquired by a 16-bit computer DAQ. So basically means data acquisition system. What is the minimum amount of onboard RAM required so that a frequency resolution of 0.1 Hz can be obtained? So this is a little complicated question, looks like, but it's not. So we have given signal frequency and the type of storage system we are using, 16-bit. Now, and we are also given frequency resolution. We need to estimate the onboard memory needed. Okay. So onboard memory is basically how many total number of bits or bytes you need to store. If we know that, then we can tell the space, memory space, storage space required, right? So do we have all the information we need? So when you are doing sampling for a signal, you need to know how long you are doing the sampling, right? So based on how long you are doing and how frequently you are sampling, the number of total data points which you are sampling is fixed. And based on the total number of sampling data points and the type of storage, you can estimate the storage space needed, right? So first, let's see what is the sampling rate. So because the signal has 1000 Hz, you need to sample it at least 2000 Hz frequency, right? The sampling rate. Okay. Now, if this is your sampling rate, then what is your time between each sample? The let's say this is the signal you are sampling. What is the sampling time interval? Is the inverse of the sampling frequency, right? So frequency is the inverse of the time. Here the sampling interval is the inverse of the sampling frequency. Okay. Now, so we know the sampling rate. Now we need to know the total time which we are sampling for. So to do that, so let's say if t is the total time we are sampling, that should be equal to number of data points which we are sampling into the time interval, right? So this is total time, this is number of samples or sampling points, and this is the sample time interval. Now we need to know the total number of sampling points to get to the storage. So how will we get the total time? Here there is one more data given, that is the frequency resolution. So the frequency resolution is actually the inverse of the total time. So which is given as 0.1 Hz here. So this means t is equal to 1 by 0.1 is equal to 10 seconds. So you are doing a sampling every 1 by 2000 seconds for 10 seconds. So then your total number of data points would be t by delta t is equal to 10 by 20,000 points. Okay. Now you have 20,000 points, and to get to the storage, now you need to look at the type of storage system. So here it is given 16 bit. Okay. So one point uses 16 bits. Okay. So that is equivalent to, if you write it in bytes, 16 by 2, 16 by 8 bytes, as 1 byte is 8 bits. Okay. So this is equal to 2 bytes. One point, storing one data point requires 2 bytes. So how many data points you need for 20,000 points? You need 20,000 into 2 bytes. So 40,000 bytes you need. Okay. And so 1 kilobyte is actually 1024 bytes. So if you convert that, 40,000 by 1024 kilobytes. So it's almost 39 kilobytes. So this is the amount of RAM needed. To store this sample, total sample. So I will repeat again once. So what we are given is the frequency in the system and the type of storage we are using and the frequency resolution. Okay. So to get to the amount of storage you need, first you need to find the total number of data points you need. So yeah. So amount of storage is type of storage and number of data points. Right. Now type of storage they have given 16 bit and number of data points you don't know, you need to estimate that. Now to get the number of data points, you need the total time during which you are taking the samples and what is the sampling interval. So this ratio will give you the number of data points. Now sampling interval you don't know it, so that is also a function of the sampling frequency, which you can estimate from the maximum frequency of the signal. Okay. Now how will you get the total time? So the total time you can estimate from the frequency resolution that is needed. Okay. So in the question they have given the type of storage, they have given the maximum frequency in the signal, and they have given the frequency resolution. So from these three we have calculated the amount of storage. So I'll give you guys 1 minute to actually try to understand this, and I'll explain one more time. Or at this point, is this clear what we did exactly? Okay, okay, thank you. What about others? Yeah. So from the maximum frequency present in the signal, first we calculated the sampling frequency as 2 into the maximum frequency. From the sampling frequency, we got the sampling interval as the inverse of it. And from the frequency resolution, we got the total time. From the total time and the sampling interval, we got the number of data points. And from the number of data points and the type of storage system, we got the amount of storage needed. So that is what we did in this question. Okay. So maximum frequency signal, type of storage, and the frequency resolution. First sampling frequency, sampling time interval, then number of sampling points, and from the frequency resolution, the total time period, and from these two, the total number of sample points, and then the storage. And the storage also, first from bits we converted to bytes, and from bytes again to kilobytes. Okay. So this way you can actually estimate or take a call on how much storage you need for the computer which you are using for the acquisitions. Okay, so this is a very simple example where you need only 39 kilobytes, but this is only for 10 seconds. Let's say you are doing this test for hours, then based on that the storage also you need to increase. Okay, so I hope this question is clear. Yeah. Uh, yeah. So let's look at the next question. What is the gain needed to amplify a signal of 1 microvolt amplitude so that a 10-bit data acquisition system with a maximum input voltage range of 10 volts can acquire the signal? Okay, so there is a signal, but amplitude is only 1 microvolt amplitude, but your storage system is a 10-bit with voltage range of 10 volts. So what is the least magnitude of signal that we can acquire in a given system? It is the resolution of the system, right? If the value is less than the resolution, then this won't come up in the acquisition. So first let's calculate the resolution for this system. So range is 10 volt and 10 bit storage system. So what is the resolution? Anyone? We did this last week, I think. Range by 2 power n, right? So 10 by 2 power 10. So resolution equals to 10 by 1024 2 power 10. Yeah. So it's equal to 0.00, if you calculate, 976 volts. Okay. Now this is the least amount of signal. So if we convert this, this would be 9.76 millivolt. So this is the least amount of signal that we can actually capture in the system. But the signal is only of 1 microvolt. So 1 microvolt, that is 10 power minus 6 volts, and our resolution is 10 power minus 3 volts. So this is actually much lesser than the resolution. So we can't actually track this signal. So if you need to do that, then you can multiply it with some gain so that it is equal to the resolution, and then it can be tracked. So 1 microwatt. So then the gain would be so is this clear? So now if you take this microvolt signal and then amplify it, this gain is basically the amplification factor, amplify it 9.76 into 10 power 3 times, then you can track that signal with your data acquisition system. Okay, is this clear? How to calculate the gain when you know the resolution and the least amplitude that you need to track? So first, based on the storage type and range, we calculated the resolution, and then we multiplied our signal with some gain so that it is equal to the resolution. Then we can calculate the gain. Okay, is this clear? Okay, I hope this is clear. Okay, so what is your doubt, Sonal? Maybe you can type it out. So let's look at some simple example like this. So your actual signal is only like this, let's say. Okay. Anyway, I'll just explain it again. Let's say this is your actual real signal, but your data acquisition system can take in this resolution only. So anything above this level only gets recorded. So only signals like this gets recorded in the DAQ system. But your real signal is very small amplitude. So what you do is you multiply this with some gain factor. So real signal into gain, so that this becomes like this, higher magnitude, so that you can actually track it. So that is the gain. So the minimum value is the resolution, so that the signal should be equal to the resolution after multiplying it with gain. Okay, so next let's move on to the next question. Yeah, I think we have a question that comes and we will discuss that. We have a question similar to that. Okay. For a DAQ system with a gain of 10,000 and a resolution of zero point 0.2 volts, what will be the minimum magnitude of signal that can be detected? So we have the gain and we have the resolution. Now the question is, what is the minimum magnitude of signal that you can detect with this gain and not with this resolution? What's the answer? Right? So real we don't know. Gain is given as 10,000 and the resolution is 0 0.2 volts. So what would be the real signal's amplitude? 0.2 into 10 power minus 4 volts. So you can write it as 20 microvolts. So now previously you can only detect a zero point 0.2 volt signal, but with a gain of 10,000 you can actually detect a signal of 20 microvolts. Okay. So this is similar to last question, but here we are calculating what is the minimum magnitude of signal we can detect. Okay. So I hope this question is also clear. Now let's go to the next question. Rajesh, that bitrate question is there. We will discuss there. Okay. Now, are the questions still now clear? How we calculate the gain and how to use the gain and resolutions? Next question is, how many factors the new resolution will be of old one by using a 12-bit memory card instead of a 10-bit memory card? Yeah. So can you answer this question, anyone? Samir or Rajesh? First, what would be the new resolution? Yeah. So for the new one, range by 2 power 12. In the old case, it is range by old one is 2 power 10. So 2 power 10. So they are asking how many factors the new resolution will be of old one. So new resolution is equal to some x into or some, let's say, some k into old resolution factor. So range by 2 power 12 is equal to k into range by 2 power 10. So k is equal to 2 power 10 by 2 power 12. So 2 power minus 2. So the new resolution would be 2 power minus 2 times the old resolution. Okay. Is this clear? So 2 power minus 2 times means basically 1 by 4. Right. So let's say if the old resolution is 1 volt, the new resolution would be 0.25 volts, better than the old one. Okay. Yeah. So I hope this is clear. Yeah. Next question. With 1024 data points, how many times FFT would be faster than DFT? So you guys remember this question from last week or the previous week also, I think. What is the number of operations needed by DFT? Order of n square, right? But FFT you only need order of n log 2n. So in DFT you need to perform 1024 whole square, but in FFT you perform only 1024 into log 2 1024. So this is almost 10 power 3 whole square, so 10 power 6. This is 1000 into log 2 of 1024 is basically log 2 of 2 power 10. So 1000 into 10, so 10 power 4. So in FFT you need only 10 power 4 operations, but in DFT you need 10 power 6 operations. So FFT would be 100 times faster, right? Okay. So is this question clear? Based on the number of data points, how many times FFT would be faster than DFT? So we have looked at this question last week also, I think. So we'll have similar problems in the last week also. Is this question clear? Okay. So yeah. Let's move on to the next question. A signal given x equal to 10 cos 200 pi t is to be captured. A minimum resolution of 10 millivolts must be the least count. What will be the optimum bit size and the sampling rate for the DAC? So they are asking what should be the storage system type for this resolution and for this signal. Okay. So I'll give you maybe 1 minute to think of an answer. So we know that bit size, resolution and the range are related, right? So we need to use that relation to come up with the bit size. Maybe I'll give you a minute to think and try solving it. So were you able to solve this? So first let's calculate the range. What would be the range here? So they have given us the signal is a cos wave. So it actually goes from plus 10 to minus 10, right? So the range is plus 10 to minus 10, so 20, and the resolution is 10 millivolt. So 10 into 10 power minus 3 volt is equal to range by 2 power n being the bit size. So 10 into 10 power minus 3 is equal to 20 by 2 power n. 2 power n is equal to 20 by 2000. So which n would be like at least has 2000, will give at least 2000. So let's try different cases. If you take n is equal to 10, 2 power n is 1024. So not enough, right? Or 10 equal to 11, 2048. So which is greater than 2000. So if you take 11-bit storage system, then you can have at least resolution of 10 millivolts, right? So this is how you can calculate based on the range, and if your resolution is given, what is the optimum bit size. So whatever value you get for the 2 power n, the n should be chosen such that it is greater than that value. Okay. Next, what is the sampling rate? So what is the sampling rate here? Based on the frequency we can estimate, right? So omega is given as 200 pi, which is equal to 2 pi f. So f is equal to 100. So the frequency of the signal is 100 hertz. So what should be the sampling rate? 2 into 100, right? So is this clear? From the signal and the resolution, based on the range, we calculated the bit size and then the sampling rate also. Okay. Yeah. Let's move to the next question. A discrete time signal x of n is equal to 10 sine pi n by 10 is quantized with a resolution of 0.02. How many bits are required in analog to digital converter in each case? Again, I think a similar question, and I'll give you guys 2 minutes to try to solve it, and then maybe if possible can you tell the answer. So here also range and resolution are given. Now we need to calculate the number of bits. Rajesh, were you able to calculate it? Yeah. So 0.02 is equal to 20 by 2 power n. Now 2 power n is equal to 20 by 0.02. So 2000 by 2, yeah, 1000. So then what should be the n for this case? Uh, if you take n equal to 10, 2 power n would be 2 power 10, which is 1024, right? So which is greater than 1000. And if you take n is equal to 9, 2 power 9 is 512. So this is smaller than 1000, and this is the next best 1024. So you should take n equal to 10. Okay. Yeah. So this is also very similar to the last question, where the range and the resolution are given. We are calculate the bit size. Next, a voltage signal with a range of 20 volts is sampled at 1000 samples per second using 12-bit analog to digital converter. What would be the amplitude resolution? So this week we have many questions on resolution. So range and the storage is given. So I think the resolution would be pretty straightforward, right? So resolution is equal to range by 2 power n. So range is given as 20 volts and storage is 12 bit. So 20 by 2 power 12 is 4096, I think. This turns out to be 4.88 millivolts. So the closest option here is 5 millivolts. Okay. So I think by now you should be able to answer this such questions on resolution, range, or if you are asked to calculate the storage system or the resolution or anything like that. Yeah, this is the question which you are asking about bit rate. So exact same question, but here we are being asked the bit rate. So this bit rate is basically when you are sampling the data, that data should be transferred to the data acquisition system. So the wires which are connecting should be, or the transmission system, whatever, wired or wireless, should be capable of sending that much data speed with that speed. So you are sampling 1000 samples per second every second, and each sample takes 12 bits because you are using a 12-bit storage system. So each sample takes 12 bits. So then how many bits you are raking up per second? 12,000 bits per second, right? So this many bits per second you should be able to store and transfer. So that is the bit rate. Is that clear, Rajesh? Yeah. So sampling frequency into storage system. So because each sample takes based on the n you are giving that many bits to store. So number of samples per second into that n will give you the total bit rate which the system should be capable of. That's it. So here we have 1000 samples per second and a 12-bit converter. So 1000 into 12, 12,000 bits per second. Okay. Yeah. Now let's do the next question. A signal x is equal to 10 sine 200 pi t into sine 204 pi t needs to be acquired. What should be the sampling frequency? Yeah. So for this case, what should be the sampling frequency? Rajesh, can you tell the answer? What should be the sampling frequency here? First, what are the frequencies that are present here? So this is 100 hertz, and the second is so what should be the sampling frequency? Yes, but uh, so that is actually wrong because you have two signs multiplied, right? So because of that, you can actually write this signal as, let's look at this formula just a minute. Cos of a minus b minus cos of a plus b. So cos of a minus b is cos a cos b plus sin a sin b, minus of cos a plus b is cos a cos b minus sin a sin b. So this actually gives cos a cos b plus sin a sin b minus cos a cos b plus sin a sin b. So this gives 2 sin a sin b. So you see we have sin a sin b, right, of that form. So that you can actually write this way. So if you write that 10 sin 200 pi t sin 204 pi t is equal to 5 into 2 sin 200 pi t into sin 204 pi t. So this is A and this is B, right? So how we can write this? 2 sin A sin B in terms of cos we can write, right? So cos of 200 pi t minus 204 pi t minus cos of 200 pi t plus 204 pi t. So this becomes, so cos of minus 200 pi minus 204 pi, so minus 4 pi t minus cos of 200 plus 204, so 404 pi t. So cos of negative is cos only, so this becomes cos of 4 pi t minus cos of 404 pi t. So now if you calculate what is FA, okay, let's do FA. This would be 4 pi by 2 pi, so this would be 2, and FB 404 pi by, let's write it as f1 f2 by 2 pi. So this becomes 202. Now what would you say as the sampling frequency? Yeah. So see, this is a tricky question. Okay, so whenever you see sine or cos multiplied, then you shouldn't directly take the frequencies from them. You should actually convert them to this addition or subtraction format and then see the maximum frequencies. Okay, is that clear? So this kind of, yeah, good. So this kind of mixing signals by multiplication is a form of mixing signals called heterodyne. So in that they actually use this only to get some unknown frequencies or to get two different waves. So basically this is from 200 and 204 frequencies which you got 404 and 202 and 2. Basically I am saying is, let's say you have two systems which can generate 100 and 102 hertz signals. Okay, from those two you are able to generate 2 and 202 even though you don't have that corresponding signal generators by mixing those two signals. So okay, yeah, so this is the sampling frequency in this. Okay, let's look at the next question. The mixer signal in the signal heterodyne has frequencies of 1002 hertz and 2 hertz. And one more thing to see here is, so basically a minus b and a plus b, right? So we can write, let's say a sine 2 pi f1t into sine 2 pi f2t as a by 2 into cos of 2 pi f1 minus f2t minus cos of 2 pi f1 plus f2t. Okay, so you don't need to do all the derivation, you can just in these cases, so the maximum frequency is f1 plus f2, so the sampling rate is 2 into f1 plus f2. You can directly do like this. Okay, now yeah, so here they have a mixed signal using this heterodyne principle which we just did, has frequencies of 1002 and 2 hertz. Now if the frequency of a known signal is 500, what is the frequency of the unknown signal? So they are saying they, after mixing the signals, they got 1002 and 2 hertz. So after mixing, what are the frequencies that you will get? f1 plus f2 and f1 minus f2, right? So f1 plus f2 is 1002 hertz and mod of f1 minus f2 is 2 hertz. So after mixing, these are the two frequencies they got, and one of the known signal is 500 hertz. So f1 is known, let's say, is 500 hertz. Then what is the frequency of the unknown signal? What is f2? Can we calculate? What is f2 in this case? So what should be f2 so that these two conditions are satisfied? So if you just do this, let's f2 is equal to 1002 minus 500, so 502 hertz, right? Is this clear? So this is one more way to get the frequency of an unknown signal. Let's say you have a signal generator, but you don't have the apparatus to do FFT. By using this signal generator, you can try to mix this unknown signal with signals of different frequencies and observe the behavior. So when f1 minus f2 is 2 hertz, such low frequencies, you will also observe beating phenomena, right? So by observing that phenomena, you can actually keep trying to to find the value of the unknown signal, frequency of the unknown signal, or unknown frequency in the signal. Okay, is this clear? What we did in the previous question and this question, Rajesh? Okay, okay, thank you. Now let's look at the next question. If two signals with the frequencies of below indicated values are mixed using heterodyne, what are the resulting frequencies and indicate whether beating will be observed or not? Okay, this is the last question. So what will be the frequencies which we will see if we mix these two frequencies? If we mix 20 and 22, what should be the frequencies? First their sum will come, right? F1 plus F2 and F1 minus F2. These are the two frequencies which we will see in the heterodyne, right? So we will see 20 plus 22, 42, and 20 minus 22, 2 hertz. Right, Rajesh? Yeah. So in the next case, 30 and 60 hertz. So then we will get 30 plus 60, 90, and 30 minus 60. So absolute value. So 90 and 30 hertz. Okay. Now if you mix 200 and 201, so you will get 401 and 1 hertz. So these are the signals, frequencies which you will get when you mix these two signals. In these three, which do you think will show beating? Yeah, this will show beating. What about first one? So there also they are very close, right? 20 and 22. So this also will show beating. But these are very different, so this won't show beating. Okay. This is the last question for today. Any doubts on today's sessions? Or any question? Rajesh, any doubts? Okay. I'll just revise once and then we can close the session. So in the first question, we looked at the sampling frequency based on the maximum frequency in the signal. So that is twice the maximum frequency. And in the second question, sampling frequency is given. So we need to find the maximum frequency that we can estimate. So half of the sampling frequency. And in the next question, we were given the accelerometer acceleration peak and the circular frequency. So from that we actually estimated what should be the amplitudes of displacement and velocity and the linear frequencies and the RMS amplitudes also, right? In the next question, we were given the acceleration graph or the signal. From that, we looked at how we can get back the displacement signal and the velocity signals. And in the next question, we were given the maximum frequency in the signal, the type of storage system, and the frequency resolution, and asked the memory storage. So from the sampling frequency in the signal, we calculated the sampling frequency. From that sampling time interval, and from the frequency resolution we got the total time, and from total time and the sampling time interval we got the number of sampling points. From the number of sampling points and the type of storage we got the total bytes you need. From that we got the total storage in kilobytes. Next we looked at what is the gain needed if your signal is actually much lower than the resolution of the system. And yeah, similar question one more. And then we looked at the comparison between two different types of storage systems and how one resolutions might be better than the other. And we also looked at how FFTs will be faster than the DFT. And next we looked at calculating the, here we are given the resolution and the type of signal. So from that we got the range, and from range and resolution we got the optimal storage system. So the optimal storage system should be greater than the maximum, greater than the value of range by resolution. And next we have a similar case to get the storage system based on the range and resolution. Next we have the resolution calculated again, and the bit rate basically based on the number of samples per second and the type of storage you can estimate the speed you need, basically the bits per second, bit rate. Then we saw how can you, yeah, in a case of heterodyne when two signals are directly multiplied in a way, how you can calculate the resultant frequencies, and then what should be the sampling frequency in that case. And in that we have a little bit more different questions in the same, we solve those. Okay, yeah. That's it for today. If you have no other doubts, I think you can log out. Thank you, Rajesh. We'll meet again next week. Thank you.